Hey guys, this is Killrob speaking, and today we are not going to do a little dev update, but instead I'm going to do what I promised, or rather threatened, in the last little dev update from the 22nd of October, where we talked a bit about engine designer calculation revamp and when it's supposed to come and what will be in it and stuff. So today I'm going to talk about that stuff and the various effects that are going to be implemented in more detail. And for those of you who haven't seen this little dev update yet and who have no clue what I'm talking about, definitely check it out first, and you will find the link right below this video in the video description. Alright, let's go over to the spreadsheet of doom. And here we are, the spreadsheet of doom. And I have edited a bit to make it a bit more user-friendly while I'm showing it off. The various effects can now easily be switched on and off, just so that we have full control over what you're actually seeing and we can discuss them one by one. Anyway, this video will be pretty large and I will be adding various timestamps to the description below if you want to jump between different parts of it. We are going to go through this list of various effects, but also we are going to build some example engines in here. And before we properly start out, I need to first say again and hammer this one home: this is not coming in the next update, but this is for further down the line when we have the Unreal Engine going, because we don't want to mess too much with the current engine calculations, but when we are porting them anyway, we can equally well do that and have that all cleared up in one go. So this is not finished, and there are various effects in here which are just missing. And one very important one which is missing is valve float. There is no valve float effect in here whatsoever. So also one important thing that is not in yet but can be modeled in here pretty simply is the various head types have different frictions in their port design. That can be put in here and will be put in here, but they are not considered yet. For example, a two-valve system like direct acting overhead cam does not have a port design which is very flowy. So that means it has more resistance and flow resistance, which would be, or let's see, mixing resonance, runner flow friction, that would be in there. And that is, for example, the advantage of a dual overhead cam 2-valve system, which has a much straighter way into the cylinder and is not as flow limited in that regard. That effect also isn't in here. To make any sense whatsoever, I should probably start out by explaining what you are seeing here. And that would be the volumetric efficiency of the engine, which is the blue curve, and the normalized power curve of that engine, or what that would be corresponding to, in red. Normalized power curve means that it will always top out at 1, independent of how much power that engine actually makes. So basically the torque curve, volumetric efficiency, is very much similar to the torque curve. And then the normalized power curve in red. Remember, some effects are not in there yet and others are not modeled properly yet. And another one of these effects missing is the year dependence and how your engineers and the various tools your engineers have got better over time. So for instance, flow optimization with computer programs was not really a thing in the 50s, I would imagine. Let's start out with something hands-on. And that would be building 3 different engine types with these different parameters we have up here. And because we are all set to some kind of standard size here already, why not start out with a mid-range engine, which we already kind of have here. So if the volumetric efficiency goes above 1, that means that into 1 liter cylinder capacity, you fill in more than 1 liter of air, and that can be achieved by not only supercharging or a turbocharger, but also via acoustic resonances. And that is a very much desired effect, and your engineers are paying quite a lot of attention to such things, especially in more high-end engines. We do have various choices here at the side, especially the intake types and the valve train type, and the exhaust type, of course. And those choices are right over to the side here. So we have various intake types. This will be a new selection in the game. Currently, this will be replacing the intake filter selection. So basically, the compact one is a standard filter. The low-end filter also has the standard filter, the mid-range has also the standard filter, the high-end has a performance filter, and the race has trumpets, and the variable one has a standard filter as well. But this selection is much more meaningful than the current one, so that should be all good. They have various effects, which we are going to take a look at later. On the exhaust side, nothing much changes, so the type here is what I put in over there, and then it automatically calculates it with these values. The exhaust types are the same as in-game right now, and they won't change either. They make a lot of sense, but they will be much more fleshed out in this version than in the game currently. So, then we of course have the different valve trains, and I know one is missing, the modern overhead valve, sorry. And that one, well, it's easy to add, but it's not in here right now. So we have the different valve train setups, and you can choose that here. A 7 would be dual overhead cam 4, while a 1 would be a pushrod engine. And then we have cam profile and the two qualities, the top end quality and the exhaust quality. And we have our 3 new sliders, the head slider, the manifold slider, and the header slider. The head slider, as I said in the little dev update, basically gives you a measure of how flowy your port and valve design is, and how large your valve area effectively is, how much you try how much valve you try to cram into that bore. So basically it scales with bore naturally. And then we have the manifold slider, which takes a look at the intake. And that is, intake manifold slider, not the exhaust manifold slider. So the intake manifold slider is determining how flowy it is. Again, 100 being very flowy and 0 being quite choked. And also how long it is. A 0 is longer than a 100, because the higher revving your engine is, the shorter it wants to have the intake to properly flow all the masses of air. And the resonances also shift depending on how long it is, how long your runners are. Then we have the header slider, which does the same thing for the exhaust end. And that is also 100 is short and very flowy, and 0 is long and not as flowy. And then engine compression, which does play a reasonable role. Let's see, compression of 6 does change the torque curve a bit, yes. Alright, and then we have of course VVT, which we will talk about when we are investigating the cam effects. You also see an absolute pressure gauge here, which currently is set to 1, meaning 1 bar, and those effects of turbocharging or supercharging haven't been completely worked out yet, but if you put it to 2, you see that in general you just get much more friction and problems with overlap, and all kinds of shit goes wrong. So that's already reasonably realistic. But as you also can see, the volumetric efficiency doesn't change as it is supposed to, and that is deliberate, because I don't want to have a graph which just resizes all the time, but one which stays in the same place. So that will be also, or that is currently also normalized to 1. The thing with turbocharged engines is that if you have 1 bar of boost, then you have a total of 2 bars, and that's the pressure absolute. So this one should be at volumetric efficiency of 2. Like, just take this times 2. But you see you are losing quite a bit in actual efficiency per boost, so to say. Like I said, we are going to start out with a mid-range kind of engine, and we are almost there, I would say. And keep in mind, there's no valve float in here right now, and some other effects are also missing. So this is basically just a flow simulation right now. Anyway, I think we are already doing pretty well, but let's investigate what happens if we, for this mid-range engine, choose a different intake manifold type. So if we go for the economy version, we see that we are kind of losing a bit of volumetric efficiency and in general moving the curve closer to lower RPM. If we do the same thing for the exhaust side, see, it takes a while. We are losing quite a bit of resonances, which you see are the bumpy things, and yeah, it's generally not that fitting to do so. If we lower the cam profile, on the other hand, that moves the cam profile more in the range of efficiency for the intake and exhaust, and you see, whoa, now we gain a lot of volumetric efficiency again, but we are sacrificing a lot of high-end flow. So this definitely is not a mid-range engine. So let's go back to free and try to optimize from there. Cam profile of 30 might be a bit low, but the mid-range, I would say, is probably around 40 cam. And then we take a look over here. That's looking very nice, this bump. We take a look over here, diagnostic tools, and that will make the current automation flow bench thing really handy, because that could directly feed in there and give you the various colors and data while hovering over, so you can really make a nice analysis of your flow. Anyway, at peak torque at 4000 right now, we do get a 5% more than 100% volumetric efficient. It is really nice, and it is of a pretty wide range as well. But we see there's quite a discrepancy between the port speed on the intake side and on the side of the header, and we want to have those for optimal flow and optimal resonances probably around the same. Because don't forget, an engine is an air pump, and if you have one part which strangles it, that lowers the overall efficiency of that engine. And if your flow is too slow, like the port speed, that also lowers your efficiency of the engine. And we are coming to that effect on the intake side later. But first, my goal is to get those to similar levels. I'm pretty happy with the port speed, but the header speed is a bit too fast for peak torque. So we are going here and we are opening up this one a bit. Header slider. This will drop down this one slightly and it will move up. Let's go to something extreme like 90. Yeah, it just moves them to a different spot, but overall this didn't really help that much. What we could do is like open up the exhaust a bit by getting more quality in there, and that generally gives us just more resonances and stuff, but that's not quite what we are after here. So let's go back to something more reasonable. We don't want to shift all the exhaust resonances off our usable power band either. What more we have here is the valve speed at peak torque might be a bit high, so we can open that one up a bit. Not 770, that is a bit bad. Let's go with this one instead, 70. And now our manifold slider might be a bit too open. So we close this down, and now you see, yes, it's a nice balance we have there now, but our torque curve is looking weird. I would definitely recommend setting your rev limiter somewhere, depending 40 cam that will probably start valve floating at around 7,500 or something. Yeah, it's about where it cuts off here anyway. So yeah, it's a bit of weird torque curve because you have this resonance bump there. Yeah, we can go with this. It has a nice efficiency in the mid-range. Gets a bit poor in the low range, but yeah, they can live with that. Alright, so let's take a look at a smaller eco engine. So first of all, we drop the bore to, say, 70. And see what that does. Just move down that one a bit. Definitely bad choice here. We go to an eco setup here. Very long intake and reasonably short exhaust there. But the cam profile we drop down to 20. And recalculate. Yes, there we go. Alright, so we have moved down the whole thing a bit. And now, let's see what we can do. We want to probably open up this a bit less. So, yeah, that's looking much better. So now we have optimized the flow for lower speeds, and we are getting to 1 volumetric efficiency at 2000, which is pretty tough because these engine sizes are not really made for good resonances down low, and you have to be a bit tricky about to actually get it down there. So yeah, cam 20, that's all nice. We are, yeah, it's decent, I would say. 2800 peak torque. That's a nice little low revving eco engine. If we drop the cam profile even more, let's see if we get something better. Now we have lost quite a bit of volumetric efficiency there, so not going to do that. But yeah, I think you get what I'm doing here. We could drop the manifold slider even a bit more and see what comes out of that. Drop it, I wanted to do. That's there. That's there. Come on, calculate. Oh, has it already done that? Alright. 10. Yes, okay, so that's definitely moving things down. And if we want to go a bit more on the cutoff there, yes, you see you can move this a lot by not even touching cam profile, which currently in automation is not possible. Basically everything is done by the cam profile alone and not so much the actual flow limiting or allowing parts of the engine. Okay. That's very good. We have our nice little eco engine, which has very shallow power curve on top and a harsh drop off there. But now let's make a very high revving engine. So we could go with a bore of 70 and a stroke of 55. And you can already see even the eco engine would be revving a lot more because it's more flowy. It has a pretty large valve area for the capacity of the engine, and that is called, of course, over square. Very handy. But now we are completely limited by all the other things here. So now we still have the eco engine, like the eco setup of the engine. We have changed the bore though. And now what happens if we put a 100 cam into it? Calculate. You see that? That is completely useless. So now we've built an eco engine which loves to rev and produces a horrible efficiency. So what can you do against that? Well, that doesn't look good. That doesn't look good. Everything looks like shit. So we are going to put something more reasonable in here. For example, a high-end intake type. Ah, yeah, much more flowy. And what would that be? Long tubular headers. That's looking much better already, but I think we are choked off quite a bit in the head. There. Yes, alright. You see where this leads. So now everything is very green, so we are maybe doing a bit too much there. Let's drop the cam profile down to 80. That's much more reasonable, isn't it? So now we are revving to with very high efficiency up to 8,000, almost 9,000. Yeah, 9,000. And then, yeah, then you have this wide band up here, which will not really be usable because of valve float coming in here, but this looks like a very nice torque curve for a high-end engine. It's climbing, 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 plateauing, and then dropping off. So, I would say we've achieved our goal, and now we just make a big one out of this and see what changes. So if you could rev this one that high, go for 80 here. You would in general way just shift down the torque curve overall for a larger engine, because it quicker goes into flow limitations and in general is not so happy about supersonic flows. So yeah, that's that. And of course it would get 120 bore, it would probably valve float before then. Alright, so that was the 3 engine types, just for showing that off, and now we are going to take a bit of a look at various individual effects and how you can steer them to benefit your engine and not limit it. Alright, so let's get into the nitty-gritty details of everything. And I've been setting this back to a very standard engine, a 2-liter inline 4, dual overhead cam with mid-range everything, and now I'm going to turn off all the effects so that we can see them individually by switching them on one by one. And as you can see, this now deteriorates to being a straight line. In volumetric efficiency, I've set the base to be at 90% volumetric efficiency, which would correspond to a torque value of 90 Newton meters per liter. Approximately. And that is our starting value, and now we just switch on the very first effect on the intake side, and that is the only one I was supposed to really model when setting out to make this spreadsheet. Hey Rob, make some intake resonances, that should be fun. Yes, it was fun. So we switch this on and see what we get. Alright, we can see that the resonances are kind of weird, as there are 2 bulges here actually. There's 2 Gaussian curves here, there and there. And then there's a bit of wiggle up on top. And these resonances are 2 different kinds of resonances. The lower frequency resonances are the Helmholtz resonators. And that is just the blowing a bottle resonance. So if you have an empty bottle and blow on top, then you will hear a certain pitch. And that pitch has only one real frequency in it. And then you have a second bulge here, which comes from that your engine is not just a bottle, but a bottle which is connected to a bottle. And what I mean with this is that you have your cylinder, which is the bottle, then you have your runner, which is the bottle neck, and that bottleneck is connected to your plenum chamber, and that plenum chamber is then connected to the outside world via a snorkel, which is another neck. And if you only have one, as the case is with intake 5, which is the race intake, let's see, there you only get one resonance and then various other resonances which are a different type of resonance. If you go for the eco setup, which has an airbox, like the plenum chamber, and you see you get 2 bigger resonances here. Of course, these are both Gaussians, and they are not really separated, as you can see. There's no big drop in here. And so the effect is, instead of having one resonance, if you add plenum chamber and an additional snorkel on top of that, like the major intake, then you split up the single frequency into 2 frequencies. One which moves slightly higher and the other one which moves down the rev range. And that is used in economy engines to get in smaller, especially smaller engines, which have a pretty high frequency, meaning higher RPM, then to shift down the peak of resonance into a economy relevant area, and that would be around 2000 RPM, where you do your cruising. So if you have a really small engine, you run into the problem of these resonances being further up as you can see here. And this is now, even with intake 2, is already in a range where you actually lose a bit of efficiency in the between 1500 and 2000 RPM. You peak around 2200. It's still good, but yeah, if you go to a mid-range intake, you will see, oh, nope, that definitely doesn't really make eco work anymore. So yeah, that is a very important effect for economy and just in general response of the engine, because if you have a big one and you put your foot down in that engine, you can see even with the mid-range intake type, you have, like from cruise, you have all the power available. And that is some of the explanation for why the American engines are so torque fanatic. With the pushrod engine design, you can just get so much more capacity in the same sized package. It's probably the main advantage of pushrod engines. And that is enormously helpful to get the grunt down low. And if we put on a pushrod head here, you will see that the resonances are moving even further down, and that is because of the design of the valves. You have a 2-valve setup, which means that you have less valve area there, which then again moves down the frequency of it. So this is all interesting and good and has a lot of emergent gameplay in that. So larger engines will naturally want to resonate lower, which makes them more grunty and less high-end, which is natural, you would say. Alright, so let's go back to a standardized 2-liter engine and take a look at what the other effect is. So this is the Helmholtz resonances. I've made it such that the compact intake, which is basically your throwaway intake, it's not even more eco than the eco intake. It's an intake which just makes sure the engine has a nice packaging, and they basically don't care about resonances. So you get one from, yeah, well, it's not really tuned or anything, but it's nice and cheap and compact and all that kind of stuff. And we wanted to take a look at the other effects, and for that we need to go to the race intake, which only has one Helmholtz resonance, which is there right now, and then these little buggers here. And these are coming from an effect which is basically playing the intake runners as an instrument. And you can see those here, as in Chrysler's Ramp theory, and that is pretty easy to explain actually. You have the intake valve opening and the air rushes in, and when the intake valve closes, then you get a shockwave forming because the air is still trying to rush towards it. It bounces off, bounces back to the all the way up to the runner into the plenum chamber, where it opens up and it gets reflected back into the runner again and moves the shockwave down towards the valves again. And this bouncing back and forth can continue a while the intake valve stays closed. And it is actually the second and third and fourth and fifth harmonic of this series, which gives you some effects. And that effect comes from when this shockwave gets back to the inlet valve, and that inlet valve is open, then the shockwave will actually see to it that you get more air in than you would by only sucking on the intake runner, with it being fully open. And quite an interesting effect. So the various, that is why the intake runner length is important. The longer it is, the lower your frequency, as in organ pipes. If you play an organ pipe, then the longer it is, of course, the lower the frequency. So that is an important effect, and we can take a look at that by just amping up the top end quality, which amplifies the effect a bit, and then giving it more cam profile, which makes the effect a bit more pronounced. No, wider. Sorry, it makes it wider, because there is more duration in it. If you up the cam profile, like the automation cam profile, the wider the longer the cam is open, the more different frequencies it accepts for boosting your efficiency. And the lower your cam profile, well, you probably can't use those up there then, especially not with race intake. That combination is not really feasible, but your resonances will get more bumpy. Anyway, you can see that there are some bumps up there, and if we now make the manifold slider longer, as in 0, then you see them moving down a bit, and if you make it shorter, these bumps are moving up the rev range. Alright, that's a neat little effect, and I think that should do it for that one. Now let's move on to looking at the others. Alright, mixing and resonance strength. That is an interesting one too. So basically this one takes a look at the speed at which the air enters the combustion chamber. And of course you are putting in your fuel into the air, and then you want to make sure that it distributes well in the cylinder. So I've just modeled an effect which sees to it if the airflow is too slow into your cylinder, then the air and fuel don't mix properly and you will have a lower efficiency for your burning. And this effect we can see right there here right now. And that is for speeds below 70 meters per second in an engine, around-ish. Normally an estimate for optimal engine speeds or optimal airflows is 70 to 80 meters a second. And with that in mind, I just modeled an effect which kind of kills it for slower airflows. And that same effect is on the exhaust side as well, which we are going to take a look at later. But now, of course, if you have a longer runner, the flow will be more limited. Because if you have, let's say you have a tiny pipe, but that tiny pipe is very short. If you apply enough pressure to it, you can still put through a lot of air there. But if you make it longer, it becomes harder and harder. And that is modeled with this effect, which limits airflow in the high end. I can switch it off again, and we can make sure that it doesn't breathe as well. So if we take intake type number 2, we know that that is pretty limiting, and then switch it on. You can see that that basically strangles it. And also if we make the manifold longer and thinner, as in 0, more eco, because it shifts the frequencies down, you can see like, oh, that completely destroys the engine breathing up on top, but might give you a nice boost down low, depending on what setup you are in. Alright, pretty strong effect overall. And then we have another very important one, and that is supersonics. If you're approaching supersonic speeds in your engine, you are kind of fucked. And why is nothing happening here right now? That is the wrong one. Alright, okay. Found a bug in my spreadsheet of doom. Easy enough, now something happens. And yes, that is the desired effect. Alright. If we switch it off again, you see, yep, that engine still breathes. That's just a normal resistance. But supersonic flows have a lot more resistance to them than non-supersonic flows. And if you're approaching the supersonic barrier, then the sound barrier that's also pressure dependent and temperature dependent and stuff, then you will run into a lot of resistance for your engine breathing. And this is not modeled entirely correctly, but the effect really is very strong and it completely strangles your engine. And then we have the little effect of the valve area, and when your cam is pressing down on the valve, that opens up a cylindric surface which the air can rush through into the cylinder. And in order to get through there, you encounter a bit of flow resistance depending on how much you open your valves. And that is determined by the cam profile to a large extent. Let's open this cam up a bit again. See, flow. Yes, okay, that's more like it. And then we just add a bit of friction in there. As in flow friction. Did that do anything? This is 1. Flow friction. mechanical friction, intake, valve friction. Yeah, it's just so low that we don't actually see it. It is very low. Because that's just such a short pipe effectively. Alright, so but this is modeling the intake resonances, the mixing and resonance strength, right? That effect I didn't address. Let me get back to that. If you are, let's see, we switch those off, right? And put on a resonant intake, like this, very good. So if you are at too low speeds, then the resonances won't work either, because if you have that, they were created by air rushing onto the closed inlet valve after it has closed, and then bouncing back and forth. But now, if you're just coming there with like 10 kilometers an hour of airspeed, there will be basically no bounce, so you will have no resonances. So this also acts not only as a mixing modifier, but also as a modifier for the strength of your various intake resonances. Alright, so here we are with the exhaust side effects, and let's take a look at the volumetric efficiency again. We are starting with our baseline of 90%, and now we have a few resonances in there, depending on the length and size of the headers. So what we are seeing here is that we are getting various bumps at different RPM, and here we don't really have a Helmholtz resonator anywhere. So it's just a kind of RAM theory, various peaks there. But the big difference to the intake side is that we have stronger effects from the primary pipe firing, sending down a pulse, and where the exhaust is collected, where the primary pipes are collecting, that pulse will be reflected back, but not only into the primary pipe, but also into the others gathering there. So you can have more different frequencies in this whole array of primary pipes being collected. And currently we have selected the exhaust type 3, which is a tubular header, which is kind of the design which does something like 4 into 2 into 1, and this kind of design again moves frequencies down. This is not accurately modeled here. This is all assuming that they are gathering at the same spot, but I'm taking a few precautions here that it doesn't become too much race everywhere by making the different exhaust resonances wider if the primary runner length, primary header length is not equal for the different header pipes. And for the exhaust type 3, where we have a staged collection of exhaust gases, I'm just moving the whole frequency band down a bit to simulate the effect what the collection of the stage collection has. Overall, that all works out pretty neatly, and an interesting effect we see here is this is 4 cylinders per bank, and like I said, the main pulse is not only traveling back in the main pipe, but also in the others, and helping to suck out exhaust gases out of the cylinder if timed correctly. That is why race exhausts, these pretzel exhausts like type 5, have so powerful resonances at some of the frequencies. They are equal length and really designed to peak that performance and suck out the exhaust gases out of the cylinder as soon as the exhaust valve opens. But that only works at various RPM, so you want to tune it appropriately with your header slider, which determines length and flow, to move them into the right location. And 0 would mean that they are moved down in frequency, and a 100 would mean that they are mainly moved up in frequency. The various exhaust types also determine the general strength of the resonances. For example, exhaust type 2 is your short cast header. That will not really give you any good resonances apart from a bit of a buff down low. If we put the header slider to like 30, you see like, it's kind of a mid-range, but not really that good. The first one, which actually gives a significant boost in resonance, is type 3, which is the tubular header. Then the long tubular would give you even more, and then the race tubular, very expensive, not mass producible, is the shit for this. And that's all good. Let's move to the second effect. That is the resonance strength. For that I turn, which I should have done for the intakes as well, but I can show you the effect here. This was this effect in the intake, the mixing and resonance strength. And if I now turn on the resonance strength for the exhaust only, then you see that if your farts are flowing too slowly, then of course you don't get proper resonance, as you know from your, holding your farts, right? So that means that there is no sound to it. If you see that effect here, it doesn't really affect it much on the exhaust side. But on the intake side, that effect is a bit stronger. Let me just quickly go back here. It starts out a bit lower, and that's why you can't really get nice resonances down low, because the airflow is just so low. Or you have you can get them down there if you strangle your engine completely up at above 4000 RPM or something. Anyway, so resonance strength is also affected by the flow, and then we have the header flow friction, which overall is just an effect of how quickly are your exhaust gases flowing through those primary pipes. And the longer they are, the more friction you get. And this is now a pretty long pipe. Let's make it even longer. And you see more friction, and if you make it shorter and more flowy, more diameter, then you will remove the friction to a large extent and have more free flow. But on the other hand, you will shift up the exhaust resonances, the rev range, quite a bit, which is maybe not a desired feature, and you want to compromise on that. Then the Mach resistance, as in supersonic flow resistance, is not really a thing for exhaust headers, it seems, because you are at such high temperature and pressure that the speed of sound is more or less double, if not more, the normal speed of sound. So you have to have really quick flowing gases in order to move into any kind of Mach resistance. So if I just switch it on here, it's doing its thing up there, which is pretty high up for this kind of setup. And for an eco exhaust, you will definitely start to see that a bit more. But if you are in race territory and have that one open quite a bit, the header slider, then that is not a big contribution at all. Everything is reset to the standard engine again, and now we are going to take a look at cam effects. And for that, first off, no, we will never be having a more detailed cam profile again. And why do I say again? Because we had it in the game, in earlier prototypes of the game, like 4 years ago. We had sliders for cam lift, for duration, and for timing overall, and overlap. And that played like shit. It was not fun, because basically what you're doing is, if you want to have a more revvy engine, you increase lift, you increase duration, and you increase overlap. So why not have it in the same slider and make it do that for you? That was just stupid, and you could really destroy your engine by it. Anyway, so and also these effects weren't really modeled that well. So we are never going to have a more detailed cam profile slider in the game. No, we won't have that. We had that and it played like shit. But what does the cam profile slider affect? Well, all of these things I just mentioned. We are going to have, or we already have in game, for a higher cam profile you have more lift, which means how far the valve pushes into the cylinder in order to let air in. or out of the engine. Then you have duration, which determines for how long the valve is open. And you would, from a just very naive standpoint, which kind of makes sense but is very static, you would estimate that, well, a valve has to be open for 180 degrees of crank angle. And yeah, that's very reasonable, because that's like the intake stroke length and the exhaust stroke length, right? That's 180 degrees each. But the engine is moving so fast that you basically have to open the valves earlier and later to make the airflow properly through the engine, and that is causing that you have durations of more than 180 degrees of crank angle. For very low revving engines, like eco engines, you still have more than 180 degrees, and you would be having something like 220 degrees or of effective opening of the intake valve, for instance. And then for really high revving engines, you would have durations of up to like 280 degrees of crank angle, which sounds kind of insane, and basically is. And that creates another thing, that is overlap, and that's why we are here. Overlap is the time, or the crank angle overlap, where both the intake and the exhaust valve are open at the same time. And that is a pretty difficult to model effect, because what happens is the intake charge is rushing down into the cylinder, and it can help you push out the exhaust gases if timed correctly and done at the correct RPM, while the cylinder is still moving up and pushing out the exhaust gases too. So if your intake charge has enough force, it will enter the cylinder while the exhaust gases are still being pushed out. Now imagine that situation at low RPM. Doesn't sound too efficient to me. Anyway, so at low RPM you have overlap losses if you are revving too low, and you have gains for overlap where this stuff actually works, where there's the correct timing for the intake charge coming in and pushing out the exhaust, and the exhaust pulses being sucked out and dragging along the intake into the cylinder. There's a lot of weird magical things going on which require very exact timing to actually work. So you get different resonances at RPM depending on your cam profile. So overlap gain, let's just look at the very simplistic modeling I've added for that. And we can, so at a cam profile of 50 you gain quite a bit for very average RPM there, where this effect works with the sizing of your valves and the lift and the duration and stuff. But then if you go to higher cam profile, this will be shifted up the rev range. And for cam 100 we find the peak at around 9,500. For low RPM engines, low cam profile engines, we find this effect at very, very weak, because there's just not enough speed to make this happen, but also at very low rev range, and you lose efficiency if you're outside of that, which we're going to take a look at now. Overlap losses are far worse than the gains you get, but if you're operating your engine in the correct rev range, then of course overlap is very helpful. Alright, so okay, I figured out what was going on there. This to actually see this effect, this goes into different other calculations. You have to turn on all the other effects, or most of them. So let me show you what this one does. The effective duration is modeled as in, when you are moving to higher RPM, the effective opening time of your valves is shortened more than what the revs would effectively say they are. And that is, if you have enough overlap, this effect will not be as strong, or not for a longer time in going up the RPM range. So if we turn this one off, you can see a slight change there for the breathing at higher RPM, and nothing at the lower end, because that's not where it's going to be limited. And another thing which comes in here is the very interesting effect of VVT. So now let's switch off all those intake side things again, and the exhaust we don't need, and we don't need those. And now you see that if we have the cam profile at 50, we have losses from overlap where the overlap doesn't work down below. We have a gain for the optimal range. This effect here, which subtracts from the duration from higher revs, that is not active here right now, so you don't see that. But if we shift the cam profile, let's say to a really racy setup, we go all the way there, we see, yeah, overlap really doesn't want to work down low, but there is a magic trick, and that is called VVT. VVT adjusts the timing of the valves such that it minimizes overlap or optimizes overlap for the for the lower revving engine, while it still allows the full overlap to occur high up where it's optimized for, and even a bit beyond that. So what happens here is especially interesting for engines that kind of want to have a bit better economy rating down low, or a bit better torque curve. And if we put it to 2, then you see the overlap effect is reduced. It's not 0, because you can't magically get rid of your and exchange your cams, right? That's VVL. That's VVL magic, not VVT magic. But you can reduce the effect of it, and depending on what kind of VVT you're choosing, that effect has different strengths. For example, if you are on a single camshaft engine where the exhaust and the intake cams are on the same shaft, then you are kind of fucked in regards to VVT, and if you choose VVT there, that will have a very small effect, which would be the 0.5 in this case. If you have them on different ones and choose the intake side only VVT, that would be this effect, and if you choose the all-around VVT, that will be this effect. Alright, looking good so far. That is the cam effects we have planned, and now let's move to a little wrap up with the miscellaneous effects. The remaining effects are just some effects which help me get rid of some extreme cases where you get efficiency where you really should not have efficiency, because these simulations, or well, simplifications really, sometimes mess up the whole thing a bit. So what I'm having here, currently I don't have a proper valve float implemented, so the high cutoff helps me to get a bit of a steeper drop depending on cam profile. This is not valve float, but it helps me see a bit more clearly what a torque curve would look like, and it's a very simple effect, as you can see here, for different cams. Nothing fancy really. We also do have an idle cutoff, and that one is actually in game right now too, and depending on what idle you have, that also depends on your cam profile of course, and how large your engine is. And if you put your cam to 50, see what effect that would have. That would move up this cutoff to higher up, where the engine gets inefficient, and at 100 you don't expect to be idling very well, so you are going to lose something already at like 2000 RPM, where you want to be cruising. Alright, so that's this effect. And now, of course, what is not properly modeled here either is the mechanical friction of the engine. And if I just put this on, I've just modeled a general linear dependence on the RPM. Now that we have gone through all these different aspects of the engine calculations, we have to take a look at where these changes will be going, and UI-wise what we have planned as well. It should be interesting for you to see. Anyway, so VVL only ever takes up 2 lines in here. So what we can do in order to get the head design slider in here is to move VVL down into this list. Also, we can get rid of the head material from this heading and make this list a bit smaller. This gives us room for the head slider here, which determines effective valve size and how aggressive, flowy your ports are. Then on here there's no changes apart from with these calculations in place. It makes sense that you are allowed to lower your variant stroke by a wider range than currently possible. Yep, no changes here really, and what we are going to change is this one though. As I already talked about in the little dev update from 2 days ago, the fuel type is not really an interesting choice. The intakes you have seen in the spreadsheet, there are more types of intake available, and that will be interesting to choose from. And for the fuel types, we have to get in the manifold slider there at this location. And the intake list will be a bit wider then. So the manifold slider here probably, and the intake choice list much longer here. Then we have on the exhaust page quite a few changes. These 2 lists become 1 slider, which is between more muffled and more open. And then we have the header slider in here, which probably should go right after the header. And that should allow for a lot more. Let's see, header slider. 1 is exchange. Yeah, that's everything we need here. Yeah, that's it basically. And all the new sliders fit in, and we have accomplished our goal at that point, once it's implemented far down the line, of removing less interesting choice like fuel type, which will be living probably here. Alright, I think that is it for this whole discussion, and I hope that was interesting in some ways. And yeah, looking forward to making the next little dev update with more news about probably then lots of balance changes. Alright guys, hope you enjoyed. See you next time.